everyone, welcome to the class, and this is Diksha Kaushal, your chemistry master teacher. And guys, today is day 2 of 5 days challenge. Yesterday we did chemical bonding from inorganic chemistry, and today we are going to do coordination chemistry. So everybody, do let me know in the chat box if you all are ready for the session, right? So guys, these two, chemical bonding and coordination chemistry, are the most important chapters from inorganic chemistry. And like yesterday, I have picked up most important topics and the sample questions related to that. And by most important topics means we are going to do what are homoleptic, heptoleptic, then what is exactly nomenclature, then what do you mean by oxidation number, the counting of oxidation number, then we will move towards VBT, CFT and isomerism. So everybody, let's start the session without wasting any time, because we have a target of completing this in next 1 hour. Let's do that, right? Okay, so everybody, right, let's start this. First is some important terms. First is coordination number. So coordination number is the number of donating sites that you have, right? That defines the coordination number. Like here the number of donating sites is 6. Here the number of donating sites, that we are not saying number of ligands, we are saying the number of donating sites. For example, there are bidentate ligands. Bidentate means which have, each ligand has 2 donating sites, like you have ethylene diamine, oxalato, these have 2 donating sites, right? So these bidentate ligands are going to, for example, you have anything that has En thrice. This, let's say there is some metal, right? There is some oxidation number here, right? Now here, this En thrice does not mean it has 3 coordination number. This means that the coordination number is going to be 6 here, right? Okay, then bidentate, then there are tridentate, which each ligand has 3 donating site, one ligand has 3 donating site, then tetra, then hexa, penta, all these are different denticity of the ligands. According to that, you will answer the coordination number. The next important term is oxidation number. So how you are going to answer oxidation number? That is, for example, you have this compound, this is X, this you should know that which one is a positive ligand, which one is a negative ligand, right? Which one is a neutral ligand. Like ammonia, water, these are neutral ligands. CN, Cl, they are negative ligand with -1 charge. If you talk about oxalato, that has -2 charge. If you talk about ethylene diamine, that has 0 charge. If you talk about ammonia and water, they all have 0 charge. So that should be on your tips, that what are the ligands which has negative, positive charges, right? So now if I say here it has -1 charge, so 4 will have -4, overall charge is -3, so X is going to be +1. That defines the oxidation number. That is written in the bracket, in the C brackets, right, in the Roman numerals, right? So here we will write it as 1 in the Roman numerals, right? Then guys, remember that primary valency, they can ask you oxidation state or they can ask you primary valency, that is the same thing. They can ask you secondary valency or they can ask you coordination number, that is the same thing, right? Now let's talk about homoleptic and heteroleptic ligands. So the complexes which have all the ligands same, that is called as homoleptic. It has all ammonia ligands. The one which has different, more than one type of ligand, that is called as heteroleptic. Now based on these basic terms, we are going to see some questions that they have asked you in recent years. 2025 question that is based on simple primary and secondary valency, that is actually a part of Werner's theory, right? So here what we have this complex, we have to tell the primary valency and the secondary valency. Now primary valency, as I told you, primary valency is oxidation state, right? So what I will try to see, firstly I will see the secondary valency. So if you see secondary valency here, coordination number will be This is En. En is bidentate ligand. So 2En means 4 plus 2 chlorine, that is, it is going to be 6. Now here coordination number is 6, right? Here coordination number is 2, 3 and 4. So it is 4, right? Here it is 4. SCN has one donating site. It is a ambidentate ligand. Ambidentate ligands are which has two donating sites, but at one point only one is donating. Like you have NO2, right? NO2 can donate from nitrogen as well, it can donate from oxygen as well. But at one point only one atom will be used in the donation, that is called ambidentate. Okay? Right? These are some terminologies that I am giving you side by side, right? Now here EDTA, if you see EDTA here, that is going to be, EDTA is ethylene diamine tetraacetate, right? It is actually hexadentate if it is -4. If I put here -4, X -4, one EDTA has -4 charge, it will be -2, that is X becomes +2. So yes, Mg2 positive is possible, that means they are talking about EDTA -4. And you know how it looks like? If you want to know the structures as well, ethylene diamine is this thing. Ethylene diamine is this thing. You have NH2 here, you have NH2. This is called as ethylene diamine. And in EDTA, you have two carbons here. This is CH2, this is CH2, this N, this is N. It is connected to acetate groups, right? That is why it is called as tetraacetate. Ethylene diamine tetraacetate. It has -4 charge here. So that's why we have put it here. Now it is hexadentate. Why? Because the lone pairs, this one is donating, this one is donating, this is donating, this is donating, this is donating, this is donating. So it is hexadentate. Coordination number will be 6 here. Here coordination number is 4. You can say coordination number is 4. Here coordination number is 4. Here coordination number is 6. Now let's talk about the oxidation number. Oxidation number in this case is going to be, if you write the oxidation number, this is X plus 0. Ethylene diamine is a neutral ligand, as you can see, that is 0. Chlorine is -1, so 2 chlorine means -2. Here you have -1. Chloride is a -1. Counter ion it is, so it is -1. So here, see, simple thing is, if here you have 1 and here you have 1. Array, wait a minute. Yes, wait a minute. If here you have 1, here you will be having +1, this will be -1. So overall the answer will be +1 here, right? Overall the answer will be +1 here. Or you know what I can do here? I'll just copy paste because we don't have that much space here. So what we are going to do? We are going to do this here. This is X plus 0 -2 is equals to +1, because this is 1, 1, so it will be +1, this is -1. So it is going to be X is equals to 1 plus 3, that is going to 1 plus 2, that is going to be +3. So here oxidation state is +3. In this case it is X plus 0 for ammonia, chlorine is -1, NO2 is also going to be -1 here. So it is going to be 2 here, right? This is overall, it is going to be 0, so X is going to be +2. Similarly, here you have, this is Hg positive +1, this is going to be -1. So it is again X, this is -4 is equals to -1, so X is equals to +3, right? This is going to be 3, this is going to be 2, and what about this one? This is, we have discussed, this is also going to be 2. So answer will be, wait a minute, answer you will see, for this coordination number has to be 6 and oxidation state is 3. 3 oxidation state, coordinations number 6, that means A is 1, A is 1, A is 1 here and A is 1 here. These two are eliminated. Now you just have to see for B. B is coordination number 4, coordination number is 4 and oxidation state is 2. Oxidation state is 2, that means B is 4. So B4 we have here, right? So answer is going to be C is the correct answer here. Okay, right everybody? That's how we are going to answer this. Let me know if that is clear to everybody or not, right? Next question is, based on similar thing, identify the homoleptic complexes with odd number of d electrons, right? Now here, what you have to do, first you have to see what are homoleptic. Homoleptic means same ligand. This is same, these are not homo, these are same, these are not homo. So we can say this is eliminated, this is eliminated. Now here you have to see odd number of electrons in D. So how you will see that? Actually that you will see from VBT, right? That you will see from VBT, that I am going to tell you soon. So let's mark it here, this one and this one, because if you want to calculate the number of d electrons, you should also know VBT theory. So these things we are going to see in VBT theory. This we will answer from VBT. Okay. Once we do VBT, I will tell you, I will again come to this question and we will answer this. Right. Then guys, this is a chart for all of you. Right. I'll give you the PPT. Now you have to go through all of this, because some students, you know, are asking that, ma'am, how I will get to know, ma'am, about that this is -1, this is -2 and whatsoever. So here you will see NO2 negative, you have SCN negative, right? Carbonyl, you can see water, ammonia, pyridine, all these are neutral. Then -2 charge are these ligands with -2 charge. Okay, so this is how you need to like revise these things again and again, so you know that what exactly you mean by this is -1, this is 0, this is -2, that should be on your tips, right? Then next category of question, very simple question that they ask you is nomenclature, right? So nomenclature, you just have to go through these rules and we will see some latest questions how they have asked you. See these rules very carefully, right? First is, always you will write cation and then you will write anion. In all the cases you will write it like that only, right? Then the second thing is, the ligands are named in the alphabetical order before the name of the central metal atom. So that means firstly you will write ligands and then you will write central metal atom, right? Okay. Names of the anionic ligands end in O, like chloride, it ends with chlorido, oxalato, bromido, right? Carbonato, right? All these are negative ligands. And if you see this here, the names I have also written here, the names of the negative ligands. Can you see the names? All of them are ending with O. So this is very important that the name will always end with O for the negative ligands. We are not talking for neutral or positive ligands, only for negative ligands, right? Then while writing the formula, these are enclosed in brackets. So like if you have, I'll just tell you this in the example, how do we write it, right? Okay, and now see this, those of neutral and cationic ligands are the same, except for aqua we have for water, amine we have for ammonia, and carbonyl we have for CO. For carbon monoxide we write carbonyl, that is CO. And nitrosyl we have for NO. These are the important names that we have. Then if you have prefixes, let's say 2 chloride, you have 3 chloride, you write di, tri. But if in the name of the ligand itself you have bi and tri. For example, you have ethylene diamine. Now in the name of the compound itself you have diamine. So if you have En tris, let's say you have En3. So you can't write it triethylene diamine. That will mean something else only. So if you in the ligand name only you have di and tri, then you will mention how much number of ligands that you have by this term, that is bis for 2, tris for 3, tetrakis for 4. For 5 you have pentakis. Okay. Then next is oxidation state are written in Roman numeral beside, next to the central metal atom, right? Then if the complex ion is cation, then the metal name in as it is. But let's see, for example, you have this as cation and this metal will be named as it is. But if this is anion, right, then this metal will have 8 in the end, right? So then cobalt will be called as cobaltate, platinum will be called as platinate, right? So if the complex ion is iron, the metal is named as it is, that is cobalt. For CO we have cobalt, platinum we have platinum. But if it is anion, then the name ends with 8. That means this will become cobaltate, this will become platinate, iron will become ferrate, silver will become argentate, right? Very important. The neutral complex molecule is named similar to that of complex cation only, but anion has different thing, right? Now, let's see the questions that we have based on this JEE 2024 question that is based on this. Let's see. So guys, if you see this here, firstly what I have to see, this is bis, right, because this is this will be trimethyl phosphine. So tri is already there in this ligand, so that's why this will be called as bis. But this one starts with T, this one starts with 3, this starts with B. So we will firstly write bromine, then we will write T, because alphabetically I have to write. So firstly I will write dibromido, then I will write bis trimethyl phosphine, right? Then you just have to, now this you have written, this is, you just have to see the oxidation number here, right? What is the oxidation number, right? This is trimethyl phosphine, this is bis bromo, this is dibromo, this is di. So this is already cancelled, this is also cancelled, this is dibromo bis tri, and this platinum, all of them have 2 oxidation states, so you will already know that you don't even need to calculate it, right? So answer will be C is the correct answer here. What about this one? Now always remember that cross multiplication is there. In front you have cation and here you have an ion. If this is 3 and this is 1, that means here it must be plus 1, here it must be minus 3, right? So firstly I will name cation. So firstly I will write potassium, 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 okay. Then here I will firstly write the ligand name, that is oxalato. So I will write not tris, I will not write, wait a minute, trioxalato, trioxalato, right? Now this is an anion, that is why this will be written as cobaltate. So answer is going to be C is the correct answer, because tris we will not write here because oxalato does not have any di, tri in its name. And cobaltate we will choose. Why 8 is chosen? Because this particular complex sphere is in the negative ion, right? So your complex entity is negative here. That is why in the central metal atom you will have 8 here. So answer will be C is the correct answer here. Is that clear, everybody? Right? Now let's talk about VBT, that is valence bond theory. Right? This is also a very, very important theory, and mixed questions are asked from chemical bonding and coordination. Right now I'll show you one question where in one question they will ask you hybridization of chemical bonding compounds as well, which are non-complex compounds, and coordination complex compound as well. So in one question they will ask you questions from 2 different chapters. So they are happy with that. Why? Because from one question they are asking you so much knowledge they are getting out of you, right? So that thing you need to take care, that if you are doing this VBT, then also you should be very good in VBT, Vesper theory from chemical bonding that I have done in yesterday's class. You can go and check that out, right? So now in the case of valence bond theory, the way we answer the question is entirely different, okay? So in this case, remember that in case of chemical bonding, we were looking for half-filled orbitals, right? But in this case, Ligand will donate to the sentimental atom. Ligand is electron donor, sentimental atom is electron acceptor. It will donate only to the empty vacant d orbitals it is looking at, right? Now, you have in your syllabus coordination number 4 and coordination number 6. Mostly they will ask you this only. Coordination number 4, if you have, there are two possibilities. Either it can be sp3 or it can be dsp2. For coordination number 6, either it can be sp3d2 or it can be d2sp3. These are the possibilities here, right? Now, if you have sp3, then it is called as tetrahedral. If it is dsp2, it is square planar. Ma'am, what is tetrahedral? This geometry is tetrahedral geometry that you have, right? Where you have 109 degrees angle between each other. That is your tetrahedral angle, if you can see, right? Tetrahedral geometry, if you can see. Then if you talk about dsp2, that has a different geometry, that is square planar. This is the square planar geometry that you have, okay? This is the square planar geometry that you have. It is making a square, but it is a planar. Then in case of sp3d2 and d2sp3, what you have is octahedral geometry in both the cases, but if you use outer d orbital, it is called as outer octahedral. If you use inner d orbital, it is called as inner octahedral. And octahedral geometry always will look like this, right? So in this case, they will mostly ask you hybridization, because octahedral is both the cases, or they will ask you outer octahedral, inner octahedral, this thing. In this case, they may ask you the shapes or geometries as well, right? Now, these are, okay, now I'll go to this one also, but firstly, let's do some questions, okay? Why I'm telling you, trust me, right? I'll tell you these are some exceptions that I have written, but I'll tell you about it, right? Firstly, you just have to know how to solve the questions, right? That I'll give you with the help of questions only, will understand how to solve, right? What is the process of solving the questions, right? So, in this VBT theory, right, when you will solve the questions regarding how many electrons in d orbital, how many electrons are paired, how many electrons are unpaired, based on that, so many different kind of questions they can ask you. And one of the question is magnetic moment, right? So if you have any unpaired electron, that is called as paramagnetic, right? So paramagnetism depends upon the number of unpaired electron. And diamagnetic is which has all electron are paired here. All electrons are paired here. If you remember, we have done this in chemical bonding as well. But the way we answer here will be different, right? So, diamagnetic complexes, how they will be called low spin and high spin, that also we'll talk about, right? Firstly, let's go to the questions, right? Now, magnetic moment, not movement, it's magnetic moment, right? Magnetic moment. Magnetic moment is under root n plus 2, where n is the number of unpaired electrons. Now, ma'am, so many things, ma'am, you have not taught us. What is low spin? What is high spin, ma'am? That exceptional chart. Let's see that, right? Okay. Let's firstly understand this question. Let's understand how to answer a particular question, okay? So, this is your JEE Mains 2025 question from the magnetic behavior of this and this. Choose the correct geometry and oxidation state. They have made it so easy for you. Now, understand one thing. There is a thing called strong field and weak field ligands. Strong field always will cause pairing. Weak field will cause no pairing of electrons, right? Ma'am, who will tell us which is strong field, which is weak field? See, strong field and weak field is actually told by spectrochemical series, which you will further study in CFT. But now what we do, we use the application of CFT in VBT. You know what was actually VBT? In VBT, actually we experimentally firstly calculate whether it's paramagnetic or diamagnetic, then okay, this is para, that means there must be no pairing, right? So paramagnetic means no pairing, right? And diamagnetic means there will be pairing, right? And based on that, the scientist gave VBT theory based on this thing, right? But in the questions, here they have given you, but you will see in most of the PYQs, they will not give you whether it's paramagnetic or diamagnetic. Rather, they will ask you in the question. But actually, VBT theory was not telling you paramagnetic, diamagnetic. Actually, you were calculating para or di experimentally, then you were applying it to apply VBT theory and to calculate number of d electrons and to calculate hybridization. But now what we do? See, simple thing is, firstly, VBT gave magnetic behavior. Then from that, we calculated hybridization. That was the original VBT theory. But now, how we solve it? In VBT, we apply CFT, that we will study further. We will only use one thing from CFT, that is strong field will cause pairing, weak field will not cause pairing, right? Then we will see whether it will cause pairing or it will cause no pairing. Based on that, we will give hybridization and magnetic behavior. This is for questions that we do. This is the original theory. This is for questions what we do, right? So we will always follow this part for the questions, right? Okay. So now assuming that they have not given you whether it's para or di, because in most of the cases they will not give you, always remember that Cl, we will study spectrochemical series. Cl is a weak field ligand, it will not cause any pairing, and carbonyl is a very strong field ligand, it will always cause pairing, right? So how do you do it? First thing is, you will make it, let's say this is NiCl4, right? And this is 2 negative, right? Here it is going to be X minus, first we calculate oxidation state. X minus 4 is equals to minus 2, X is equals to plus 2. Then nickel, we know that nickel 28 atomic number, it has 4s2 3d8. When you take out 2 electrons, you take out 2 electrons from 4s, so it will become nickel 2 positive will become 3d8, right? Now you know that for 4, either the answer can be sp3 or the answer can be dsp2, right? Now if you see this here in d orbital, what you have here, in d orbital, what you have here, you have 8 electrons. Now chlorine is a weak field ligand, it will not cause any pairing, so that is why it will be 1, 2, 3, 4, 5. Firstly, all the degenerate orbitals will be singly occupied. 5, 6, 7, 8. Can you see now what you are left with? The empty orbitals are this one. You will not look for the half filled, only empty. This is sp3, so this is going to be tetrahedral in nature. And if you see, number of unpaired electron is 2, so mu is going to be 2, 2 plus 2, that is going to your Bohr magneton. And always remember, I am giving you a simple trick for the magnetic moment, that if you have number of unpaired electron, if number of unpaired electron is 1, number of unpaired electron is 2 or 3 or 4 or 5, then you don't need to even calculate this thing. Just put it 1.7, put 2.8, this is 3.8, this is 4.9, this is 5.9. 7, 8, 8, 9, 9, just put the points here and you will get your answer. So this is going to be, they can also ask you the magnetic moment here, that is going to be 2.8 Bohr magneton here, right? Okay, then you have NiCO4, right? You have NiCO4. Now you should know some really basic things about this chapter. X. Now carbonyl is a neutral ligand. It will have 0, that I have given you chart. You will understand from there which is neutral, which is negative. So X plus 0, overall charge is 0. So nickel will be in 0 oxidation state with 4s2 3d8. And we know that carbonyl is a strong field ligand. Right here, this one is ruled out, this one is selected. Coordination number 4 can give you either sp3 or dsp2, right? So now if you see this here, this will be d orbital, this is s and this is p. Total number of electrons that you have here is 8 plus 2, that is 10, and this is going to cause pairing, so it will be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and again the answer is going to be sp3, that is tetrahedral. But here this is a paramagnetic complex, this is a para because it has unpaired electron, and this is a diamagnetic complex with mu is equals to 0 because unpaired electron is 0. So answer is going to be Cl4 has Ni2 positive, Ni2 positive, Ni2 positive, it is tetrahedral. This has Ni this, and this is B is going to be the correct answer here, right? Okay everybody, now let's see. Okay, I also want to tell you one more thing. We discussed about low spin and high spin. Ma'am, what do you mean by low spin, high spin? See, simple thing here you can see, here it is causing the pairing, here it is not causing the pairing. So you have spin here, this is unpaired, this is unpaired. So that means the spin you have here, unpaired electron you have here. Whenever there is no pairing, that means you will have spin, that means it will be high spin complex. This is going to be high spin complex, and here because of the pairing you don't have any spin which is not cancelled by the other thing, that is why it is a low spin complex, and that is the reason we have written here that in case of diamagnetic, when you don't have, when all are paired, that is a low spin complex because there is no spin that is not cancelled by anything. In case of paramagnetic, you have a high spin here, right? Okay, yes everybody, do let me know if that is clear. Now this is a question that they have asked you in JEE 2024, and as you can see, this is entirely based on this thing that chemical bonding, this is from chemical bonding and coordination both, right? These are the compounds that we have discussed in yesterday's class. I'll just answer it. Now, if you have not gone through that lecture, then do go through. It is also 1 hour 15 minutes lecture only. So here this belongs to group number 15. So 5 valence electron minus 5 is equals to 0 lone pair. So sigma bond is 5 plus lone pair is 0. So it is going to be sp3d because overall steric number is coming out to be 5. Right? In this case, what you have, this is belonging to group number 7 minus 5. So it is 2 electron means 1 lone pair. Right? So you can say sigma is 5, lone pair is 1. So it is 6. That means it is sp3d2. So this is going to be false because BRF5 is coming out to be sp3d2 and this is coming out to be sp3d. Those who are not able to understand this, guys, this we have picked from chemical bonding. This statement is a question from chemical bonding. I just want to show you that a mixture of chemical bonding and coordination chemistry is also asked to you, right? Okay. Then if you talk about SF6, it's also a very famous compound. Sulfur belongs to group number 16. That means 6 valence electron minus 6, it is 0 lone pair. So sigma bond is 6, lone pair is 0, it is going to be 6, that is sp3d2, right? Okay, what about this one? What about this one? Okay, let's see this. Now always remember, ammonia behaves as a strong field ligand, right? Only in some cases it will behave as a weak field ligand. I will just show you the exceptional case here, right? This is the time for exceptions. Right? Okay, I'll just show you the exceptions here. If you see, cobalt 3 positive is bonded with water and oxalate. These are, if you see with ammonia, do we have any exception? Do we have any exception? 3D series elements in plus 2 oxidation state form outer octahedral complexes up to ammonia. I think we don't have any as such exception with ammonia. This act as a weak field ligand, yes. So actually with Fe2 positive and Mn2 positive, this ammonia behaves as a weak field ligand, otherwise it's a strong field ligand, right? So here this is a strong field ligand. Ammonia is a strong field ligand. Achha, I'll tell you one more thing here. Chalo, firstly now just remember that ammonia is a strong field ligand. Why whatsoever that we'll talk about in spectrochemical series. For now, just remember this is a strong field ligand, right? Okay. So now we know that here it is x plus 0 is equals to plus 3. So cobalt, which is 4s2 3d7, right, with the atomic number 27, cobalt plus 3 is going to be 3d6. 2 electron from here, 1 from here. Now you will have this S and this as P. Now if you see, when you fill the electron, that's a strong field ligand, 1, 2, 3, 4, 5, 6. So answer will be, you will be left with D2sp3. You will be left with D2sp3. That is going to be the answer here. So here it is going to be D2sp3. So this statement is also a false statement. So we can say both the statements are false. So answer is A is the correct answer here. Right, everybody? Answer is A is the correct answer here. Right? Now, one thing I want to tell you that actually we will study in spectrochemical series. Okay? Let me just show you spectrochemical series. Okay? This is actually we'll study in CFT. This is an application. This is actually a conclusion of CFT. This was given by CFT. Right? So, if you see this theory, carbonyl is strong field, Cn is strong field, C6H5 strong field, CH3 strong field, NO2 strong field, right? Fen, biphenyl, En strong field. Till here, all of them are very strong field. There is no question about it. They will always behave as strong field, right? And ammonia will, most of the cases, it will behave as strong field, but there are some exceptions as well. Because VBT theory has a lot of exceptions, right? That is why, again, we have to come up with a new theory. Why? Because that was not a successful theory. So that is why usually these halogens, they are behaving as a weak field ligand only, but there are some exceptions, and that is why these exceptions I have written here. Right, what you will see here is all the exceptions that I have written here, that I will do one by one. Now if you see water and oxalate, that was before ammonia, and before ammonia all the ligands are behaving as weak field only, right? But for cobalt 3 positive, they are behaving as strong field ligand. This is a very important point. Then Cu2 positive is bonded with water. Then also water is behaving as a strong field ligand, right? Then guys, we have nickel 4 positive. It will make fluoride ion a strong field ligand, which is actually a very weak field ligand, right? Then Fe2 positive and Mn2 positive will make ammonia a weak field ligand, which is actually a strong field ligand, right? Then remember that 3D series in +2 oxidation state always form outer octahedral complex, that means sp3d2 they will form. sp3d2 is usually formed when there is no pairing, right? So 3D series in +2 oxidation state, before ammonia all the ligands are behaving as weak field ligand, right? Okay, before ammonia in the spectrochemical series all the ligands in +2 oxidation state are behaving as weak field ligand. Weak field ligand. That is why they are forming sp3d2, right? Compounds of 3D and 4D and 5D series. If you have 4D and 5D series, 3D series, though some will behave as strong, some will behave as weak. But in 4D and 5D series, no matter whatsoever is the ligand, they will always behave as strong field ligand. They will always behave as strong field ligand, right? Especially in the case of coordination number 4, right? So these were some of the important points. Now let's see this question that is entirely based on magnetic moment. It says that the calculated spin only magnetic moment of this and this you have to tell. Now firstly I will tell about this one and then this one. If you see this here, it is going to be 3 and this is minus 3, this is 4 and this is minus 4. So it is going to be x minus 6 is equals to minus 3, so x is equals to plus 3. This is x is for iron minus 4, this is minus 6 because OH is 6 here, right? As you can see, this is 6 here, okay, is equals to minus 4 because this is 4, this means this is minus 4. So here it will be x is equals to plus 2, right? So here iron is plus 3, this is plus 2. So iron actually it is 26 atomic number. So iron plus 3 is nothing but it is 3d5. Iron plus 2 is nothing but it is 3d6. Now OH negative is actually a weak field ligand, right? OH negative is actually a weak field ligand. It is not under the category of strong field ligands, right? So what you will see, it will not cause any pairing. So what you will have 1, 2, 3, 4, 5. Number of unpaired electron is 5 here. That is the reason mu will be equals to 5.9, right? And in this case, what you will have, here this is equals to 1, 2, 3, 4, 5 and 6. Here what you will have is 4 unpaired electrons. That is why mu is going to be 4.9. So answer is 5.9 and 4.9 is the correct answer. So C is going to be the correct answer here. Right everybody? C is going to be the correct answer here. And these magnetic moment questions are very, very important, right? In inorganic chemistry, they plays a very important role. Now, these are some examples that I have written. Majorly do for sp3, dsp2, d2sp3 and sp3d2, right? Because they are not asked, they are also not asked, they are also not asked, right? But still, if you are like, ma'am, I totally want to be risk free, then you can do that, but most probably they will not ask you that, right? Okay, yes everybody. Okay, now let's see next theory, that is CFT theory. Tell me everybody in the chat box if you are ready for CFT theory, right? Crystal field theory. Crystal field theory. Let's see that. See, 40 minutes we have done. Let's see. I think more 20 to 25 minutes I'll need to complete the chapter, right? In CFT theory, that is called as crystal field theory. Crystal field theory. So basically it works on that it is ionic interactions between ligand and metal. So ligand and metal interactions should be really good. This is said by this theory. So what will happen? It says that we will see for octahedral and tetrahedral different things. So what will happen? Firstly, you will have all the orbitals at degenerate. When the ligand is approaching, they will become very happy. They all will have rise in their energy. So basically, two types of interactions are working when ligands and metals are getting attracted. First is attractive force, because we take ionic interactions here, electrostatic interactions, that says that ligand is negatively charged, it is electron donor, and metal is electron acceptor, right? That is like a cation, so they will have electrostatic interaction. That is the attraction. Then when they come really closer, when they are at this point, till now attraction was there. Now there will be a force, that is repulsive force, between the d electrons of metal, because metals will have d electrons, and the electron donor electrons from the ligands, because ligands are donating because they have extra electrons. So electron and electron repulsion will be there, and that is why splitting of d orbitals will take place. Now in this splitting, what will happen? There is a thing called Berry center. Berry center is the level that when they were all degenerate with high energy. Now what will happen? From the Berry center, the amount of energy that increases and decreases, that we will define. So because dx square minus y square, dz square, they are along the axis, and octahedral is also along the axis. So that is why repulsive forces will be more in case of dx square minus y square and dz square. That is why here you will see the rise in the energy, stability will be less. Here there will be decrease in energy. These are called as EG, and these three orbital dxy, dyz and dzx are called as T2G. The distance that you have from the berry center, it is plus of 3 by 5 delta naught. This is minus of 2 by 5 delta naught, because here the energy has decreased, right? Now, see one thing, that here you can have different things. You can have addition of 1 electron, 2 electron, D1, D2, D3, so many things can be there. Remember that whenever you have one, whether it's strong field or it's weak field, doesn't matter. If you have two, whether it's strong or weak, doesn't matter. If you have weak field, see, whether you have strong or you have weak, in strong field you will cause pairing. But for pairing also, right, what should happen? For pairing also, firstly, degenerate orbitals will be fully filled, right? Okay, so strong field, weak field will not work here. Because actually, you know what happens? Why something is strong field, why something is weak field? Strong field ligand means the one which has such a big field that the gap, this gap is very large in case of strong field ligand. So that is why when you fill one electron, second electron will be filled here, third electron will be filled here, whether you have small gap or you have large gap here, right? But fourth electron has a choice. If you have very small gap, if this gap is very small, then fourth electron will go here. If this gap is very large, then fourth electron will go here, right? Okay. So D1, D2, D3. They will have same, doesn't matter it's weak field or strong field, right? If you have D4, right, D5, D6, D7, they will have different from strong. If you have like D5, 1, 2, 3, if you have strong field, then pairing will take place, so it will be 4 and 5. If you have weak field, then it will be 4 and 5, right? If you have, let's say, D7, it will be 1, 2, 3. If you have strong field, it will be 1, 2, 3, 4, 5, 6 and then 7. If you have weak field, it will be 1, 2, 3, 4, 5, then 6, 7. It is different. But if you have D8, it will be 1, 2, 3. For strong field, it is 1, 2, 3, 4, 5, 6, 7, 8. And for weak field, it is 1, 2, 3, no pairing is there. 4, 5, then 6, 7, 8. It is same. So, in case of D8, D9 and D10, strong and weak are same. Strong and weak are same. You can just write it here. In these cases, strong and weak are same. And you know what, there is some other name for strong and weak field as well that we will talk about. But firstly, let's see tetrahedral field, what happens. In tetrahedral structures, what happens? Same thing will happen till here. But when you talk about which orbital will have increase in the energy, that will be dxy, dyz and dzx. They will have increase in energy with plus 2 by 5, and they will dz square and dx square minus y square will have decrease in energy with minus of 3 by 5 delta t. And always remember, delta O splitting energy is always greater than this. Delta T is approximately 4 by 9 of delta O. That is very, very important, right? Okay, delta T is almost half of delta O, right? Okay. Now, there is some another way of writing strong field and weak field. Let me just write it here. Strong field, you know how you can write it differently. You can also say, in case of strong field, the gap, CFSC, gap is high. Strong field means the gap is very high. Gap high means it will not be able to jump to the next orbital, so it will cause pairing. So that is why it is causing pairing. Now it is causing pairing. That is why the half spins will be less here. So that is why it is called as low spin complex. Low spin, or it is also called as spin free complex. Spin free complex. They all mean the same thing. They all mean that you will do pairing here. They all mean the same thing, right? Because different names are used. That's why I am writing this here, right? And then one more thing they can say, that when it is causing pairing, see, when you are, let's say you love this t-shirt that you have seen on Amazon, you're like, I want to purchase this, but that t-shirt cost only 200 rupees and you have 200 rupees. You're like, okay, I can purchase that, right? So now that means the pairing energy is actually less than the money that you have. So you had delta of money and pairing energy is less. That is why you are able to cause pairing, right? But in case of weak field ligand, things will be different. In case of weak field, CFSC gap will be low. That is why they are causing no pairing. They will jump to the next orbital, right? And they will be high spin complex. That is also called as spin paired complex. Wait a minute. Here you will, I am so sorry. This will be spin paired complex. Okay, spin paired complex. And this is going to be spin free complex. Spin free complex, right? Because more spins will be there. High spin is there. Now in this case, because you are not able to purchase, let's say that t-shirt is for 2000 rupees and you don't have that, you will say, I would rather purchase a test series or something rather than purchasing a t-shirt for that, right? So that's why you'll be like, no, I will not purchase this because the pairing energy is greater than the money that you have, right? So these are the things that you must remember. These are the hints that they can give you in the question, right? Okay. Now let's talk about a formula that we have here, that is CFSE is equals to minus 0.4 number of electron in T2G plus 0.6 number of electron in EG delta O plus N star P. What is this N star here? N star means the number of pairs that you have. Let's say you have D4. In case of D4, if you see, in case of D4 it will be 1, 2, 3, 4. When you don't have CFT, it will be 1, 2, 3, 4. That means no pair will be there. Let's say you have D6. Let's say you have D6, okay. In case of D6, if you take simple, it will be 1, 2, 3, 4, 5, 6. One pair is there. But when you say strong, it is octahedral and this is, let's say, strong field, right? Now you have 1, 2, 3, 1, 2 and now here you have 1, 2, 3, 4, 5, 6. Here you have 3 pairs. So N star will be the number of pairs that you have now and the number of pairs that you have before, that is 2 is the extra pairs that you have. That's why N star is number of extra electron pairs formed because of ligands in comparison to normal degenerate configuration. This is normal and this is extra pair is 2 extra pairs that you have here, right? Okay, now let's talk about questions based on CFT theory. So based on CFT we have questions. Let's talk about that, everybody. Let's talk about that. Now in case of these things, first thing is you will have this one, this one, this one, this one. I'll fast forward, I'll do this, right? This is X plus 0, this is titanium plus 2, this is vanadium plus 2, this is manganese plus 3, this is iron plus 3, right? If you see this here, they are all octa and they all have weak field ligand, right? Now here if you see, titanium plus 2 is actually 3d24s2 because 2 electrons you will take from 4s, right? And here when you see, it will be octahedral complex, so it is going to be 1, 1, 2, 3, 1, 2 and electrons will be filled like this. 2 electrons you have, 1 and 2 electrons will be here. So T2G 2, EG is 0, so CFSE will be minus, this will be multiplied by minus 0.4 and this will be multiplied by 0.6. and no paired electron is there, so we are not going to add any n star here. Answer is going to be this. For B, that is vanadium, we have this as an electronic configuration. We'll see that how do we fill the electrons here. Vanadium has 3 electrons here, so it will be 1, 2, 3 electrons in T2G. So 0.4 into 3, 0.6 into 0, delta naught, that is, this is the correct answer. Next is for manganese, what you have. In this case, manganese 3 positive, this is the electronic configuration. How do you fill it? This is 1, 2, 3. This is a weak field ligand. So it will be 1, 2, 3 and 4th electron will go there because weak field ligand means gap is very less. Right? So it is T2G is 3, EG is 1 electron. You will multiply this by 3, multiply this by 1 and you will have the answer. Then you have FeH2O6. Iron has this electronic configuration 1, 2, 3, 1, 2. How do you write the 5 electrons here? 1, 2, 3. Now this is a weak field ligand, that's why other 2 electrons will go in the higher orbitals. So it will be T2G has 3, EG has 2, you will put the values here and you will get the answer, and they are asking you to match the following. You do that and you will get your answer as correct. A is the correct answer here. Right, then guys, this is the spectrochemical series that I have talked about, right? This is how these are all weak field ligand, then here you have all the strong field ligands. This is strongest is carbonyl, then you have CN, then you have NO2 negative, EN, NH3. So this series you must remember, because based on this series as well they ask you questions like this, that is JEE Mains 2025 question. That is exactly based on this series. They say the correct order of complexes, this you have to tell, right? And in terms of wavelength, now C E is equals to HC by lambda. So energy is inversely proportional to lambda. All you have to see is that means delta O is inversely proportional to lambda. So what is the order of, this is only ammonia, this is ammonia 6, this is CN. So CN is strongest, so it will be C. C has maximum delta O. Then you will have ammonia, that is 6 here. है ना? Ammonia 6 here. B. Then you will have, here you have ammonia 5 and Cl, here you have ammonia 5 and H2. So H2 is stronger as compared to Cl, so it will be A and then it will be D. Opposite is going to be for the wavelength, so answer will be CBAD. C is less, then B, then A, then D. So answer is going to be C is the correct answer here. So all you need to do is spectrochemical series. That should be on your tips and you will be able to answer that, right? Now next thing is guys, metal carbonyl. This kind of question also they have asked you multiple times in the latest years. Now metal carbonyl actually has a synergic bonding. We know that metal is supposed to gain the electron. Gain means it is supposed to accept the electron. Ligand are supposed to give the electron. So metal and ligand, they will have sigma bond where ligand is donating to the metal. But metal will be like, bro, you are giving electrons to me. I also have d electrons, so I will also give electrons to you, and that is pi back bonding. This bonding that I have shown by red line, that is pi bonding, back bonding, synergic bonding for the carbonyl complexes, right? When metal accepts the electron, it accepts the electron in the sigma bond. That means when the ligand donates the electron, it is by sigma bond. And when metal donates the electron, it does so in the anti-bonding orbital. It does so in the anti-bonding pi star orbital of carbonyl. So electrons are accepted by the ligand not in simple orbitals but in pi star anti-bonding vacant orbitals of carbonyl. This is a very important point to remember. You don't have to go through the MOT diagram, just remember this one. That is accepted by sigma but it is donated in the pi star anti-bonding orbitals, right? Now these are some really important structures that you have for carbonyls like NiCO4, FeCO5, CrCO6, right? Then you have manganese, manganese CO10. Then you have, this is very, very important, okay? These are very, very important structures, right? These are directly from your NCERT, and if you see, questions has been asked directly on the structure. This is JEE 2024 question, and you will see how question they have asked. In which of the following metal carbonyl CO form a bridge between metal and atom, right? So if you see, all these are very important for you, right? Bridge, CO should form a bridge. CO should act as a bridging ligand here, right? So if you see this here, right, where CO is acting as a bridging ligand, only here. Here it is not acting as a bridging ligand. Here no CO is in the bridge, no CO is in the bridge. All are connected to the metal. Here it is connected to the metal but as a bridge. So answer is going to be D is the correct answer, and this question is very, very important, that in cobalt carbonyl complex you have two bridging carbonyls, other are terminal. These 1, 2, 3, 4, 5, 6 terminal carbonyls you have, only two bridging carbonyls you have here. Then the same kind of question they have also asked in JEE 2023, that is, if sum of bridging carbonyl in this and this would be. Now in case of, if you see manganese, this is manganese, can you see any bridging? No. In case of tungsten also there is no bridging. I have already drawn the structure here. There is no bridging ligand in case of tungsten as well. So that is why the answer is going to be 0 is the correct answer here. Is that clear, everybody? Tell me. Now we are moving towards the last topic of today's lecture, that is isomerism, right? Okay, everybody, last topic of today's lecture is isomerism. See, in case of isomerism, guys, we have two kind of isomerism. One is structural, other is stereo, right? Structural isomerism is actually the for example, the linkage, how the bonds are connected with each other, right? The rearrangement of the bonds can be there. But in case of stereoisomerism, the spatial arrangement will be different. The linkages will be same. So firstly, let's talk about structural isomerism. You have ionization, hydration, coordination, linkage, ligand and coordinate position isomerism. So let's see this one by one. What is ionization isomerism? Where the difference, I hope so you're able to see this. If you see these examples, this counter ion is interchanged by the ligand. This is acting as a ligand here. Now here it is acting as a counter ion. So that give different ions in the solution. That means different counter ions they are giving, and the same counter ion is behaving as a ligand. That is called as ionization isomerism. Next is hydrate or solvate isomerism, in which the number of water molecule acting as a ligands are different. Here 6 water molecules you have, here you have 5 water molecules. And considering that they all will have same molecular formula, right? Linkage isomerism is when you have ambidentate ligand. Ambidentate ligand like you have NO2 and ONO, where they have two donating sites, but at one point only one will be taking part in the donation. So here you have nitrogen is taking part in the donation, here oxygen. Rest of the things are same. That is linkage isomerism. Then coordination isomerism is when you have two coordinate spheres, and what you will see here in these two coordinate spheres, cobalt is connected with ammonia. Here cobalt is connected with Cn. Here chromium is connected with Cn. Here chromium is connected with ammonia. So here what you have occurs when both positive and negative ions are in the complex, both have 1,1 complexes. Two isomers different in ligand distribution. Ligand distribution is different in the case, right? Then guys, we have ligand isomerism. In case of ligand isomerism, what you have, the ligand already is a isomer of each other. In one complex you will use this, in other complex you will use this. when the ligands are, you have two different ligands in two different complexes and both are the isomers of each other, like these are isomers of each other, right? Then there is coordination position. In coordination position, it occurs in case of when you have two metals or more than two metal ions, right? More than two metal ions you have, and this metal ion has 4 ammonia and here it has 3 ammonia and 2 Cl. But this metal ion has 3 ammonia 1 Cl, 3 ammonia 1 Cl. That means this occurs when you have more than two metal ions, and in both the complexes the distribution of ligands to the metal ion is going to be different, right? That is coordination position isomerism, right? Okay. Next guys, we have stereoisomers, right? Stereoisomers, actually I have done a 3-hour long lecture on that. If you have never gone through stereoisomer, that would be my advice to you. Guys, if you have never done stereoisomerism, I have taken it here because it is very important, right? But if you're like totally blank, ma'am, I'm doing it for the first time, I would advise you go through my 3-hour long lecture, right? Firstly, go through that, because if you want to understand, you will be only able to understand in 2-3 hours. It will take you to understand this concept, right? But otherwise, if you're here for just revision, ma'am, okay, I just want to just revise that what exactly was there, ma'am, I don't remember anything, then you are on the right platform, right? Otherwise, search Diksha Ma'am, stereoisomerism coordination chemistry, JEE Vedantu. You will have your 2 months back I have taken that lecture. Go through that, right? If you've never done this, right? Otherwise, let's see. Now this is divided into two categories. One is geometrical, other is optical. Geometrical is only shown by square, planar and octahedral. Optical is shown by tetrahedral and octahedral, right? So first we will talk about geometrical isomerism. And before starting this, always remember that if I say that there is AA or BB, that is called as symmetrical. Whenever I write bidentate ligands, like I mention it by AA, BB, CC, that means I am talking about symmetrical bidentate ligands that has two donating sites, like ethylene diamine or oxalato, that are symmetrical. If I say AB, then I am talking about unsymmetrical ligands like these. This is donating from N, this is donating from oxygen. They are unsymmetrical bidentate ligands. Okay. Now let's talk about, ma'am, what is cis and trans. Geometrical isomerism means cis and trans. Cis means when two same ligands are next to each other. Trans means when two same ligands are opposite to each other, right? Now let's talk about coordination number 4. See, tetrahedral complex is not going to give you geometrical isomerism, because here you can't say this is opposite to this one, or this is opposite to this one, or this is opposite to this one. You can't define cis and trans here. That's why tetrahedral will never show you any cis and trans, right? So we'll talk about firstly square planar, then we will talk about octahedral complexes. In case of square planar, I have directly written that all these category of complexes will never show you any geometrical isomerism. You have A4, A3B, AB3, AA2 means two symmetrical bidentate ligands you have, then two different symmetrical bidentate ligands you have, you can't define it. One symmetrical and one unsymmetrical bidentate ligand you have, they will never show any geometrical isomerism, right? But if you talk about MA2B2, right, this is going to be cis because they are next to each other. Here Cl, Cl are opposite to each other, that is trans, right? So it is showing, and here cisplatin. Cisplatin is a anti-cancer drug, right? That is used. That is a very important question, right? And this is a complex of PTNH3 twice Cl2. Then Ma2Bc, in this case A and A are next to each other, so it's cis. A and A are opposite to each other, so that is trans. Here also we can define. Then if we talk about this one, is very important. In this case you have MABCD. Now see this, how to define this. Firstly, now this is actually a way to define this one. This is A, this is B, this is C, this is D. Now I am going to fix one of them. Let's say I fix this one. Okay. Now I'll draw two more diagrams where I'm going to fix the position of A. Right. This also I'm going to fix the position of A. Now I'll interchange these two. This will be D and B and this is going to be C. I'm going to interchange these two. This will be B and C here. This is B and this is C. This is going to remain D only. Right. Okay. Now in this case, what you will take, you will assume that any two of them is same. Like in this case, bromine and chlorine I'll take as same. Why? Because bromine and chlorine belongs to halogen, so I'll take these two as same. Right. So let's say in this case you say, ma'am, B and C, ma'am, take B and C as same. This will become trans. Ma'am, take B and C same in all the cases. So this will become cis. This will become cis. So always you will have two cis and one trans. Let's say, ma'am, I don't want to take, ma'am, B and C as same. Ma'am, I want to take, ma'am, A and B as same. So if you take A and B as same, this is cis. A and B as same, this is trans, this is cis. So always you are going to have, no matter what you take, always you are going to have two cis and one trans in this case, right? Okay. Now if you have AB2, that means two unsymmetrical ligands that you have. In that case, AA, they are opposite, that is why it is a trans. And here AA, they are in front of each other, that is why it is a cis. Okay. Then if you have coordination number 6, in this case no GI will be shown by if you have MA6, MA5B, MAB5 or MAA thrice, they will never show any geometrical isomerism whatsoever. Right. But let's talk about the one that shows GI, MA4B2. This is very important case that is very frequently asked. Now here Cl and Cl are next to each other, so that is cis. Here Cl and Cl are opposite to each other, so that is trans. Okay. A3B3 very important. In this case now I'll have to show you the diagram as well. Now see, there are two, this is also specially mentioned in your NCERT, that's why this is very important, right? Now in this case, see, two A3B3, you have two kind of complexes, one is facial, one is meridional. Facial isomer is when on the one phase of this octahedral, this is one triangular phase of the octahedral, you have same ligands, right? And how you draw it in 2D? In 2D you draw it next to each other. A will be next to each other and B will be next to each other, right? Acha. Ma'am, what is meridional? Like facial, same ligands are on one phase, same ligands are on one phase. That's why it is called facial isomerism, right? And if you talk about meridional, here same ligands will be forming a semicircle, that is C. Can you see the C here it is forming? Can you see this C here that this one is forming, right? This one is forming this C. Can you see that? So it is forming, same ligands will be forming a semicircle. How do you write it in 2D? A, then one gap and then you will have A. B, then one gap, then you will have B. That is meridional and facial isomerism. This is very important. Okay. Then you have A4BC. In case of A4BC, we can see this here. In case of A4BC, how do you see? Here in this case, if you see, C and B are next to each other, right? That's why we are saying that it is behaving as a cis, right? Okay. And here C and B are opposite to each other. That's why this is behaving as a trans. Okay. So we are approximately taking these are equal, and that's how we can define that which is cis and which is trans. Okay. Because with A we can't define it. With A everything is next to each other only. Right. Okay. Yes everybody. So next is going to be MAA twice B2. These are two symmetrical bidentate ligands. When the symmetrical bidentate ligands are next to each other, that is cis isomer. When symmetrical bidentate ligands are this and this is opposite to each other, that is called as trans isomer, right? Then these are, guys, the full like chart that you have for the number of geometrical isomerism. Here this one is very important. If you don't want to remember all of them, just remember MA2, B2, C2 and MA, B, C, D, E, F. That is 15. These are very important. Okay, these two we have seen already, right? This is the full chart because there are so many different kind of GI. So you can go through this chart as well here, this chart as well here, right? Okay. Now let's talk about optical isomers. You must have studied about optical isomers in organic chemistry as well, but here we'll only study about the POS, right? So you just have to identify the one that does not have any POS. If POS is not present, then optical isomerism will be present in this case. And optical isomers will be enantiomer of each other. One will be dextro, other will be levo. And they will be non-superimposable mirror images of each other. They are called as optically active, right? And they are the enantiomer of each other, right? And yes. Now, here I have given you directly because I know that, guys, as I am telling you, otherwise this actually topic is, I don't think so anyone can complete it in like 15 minutes. It's not possible, right? So I have specially taken this lecture of optical isomerism. That is very important. I have in detail covered all of these things, why this will show PS, why this will not show POS, everything I have covered. But here I have just given you the conclusion part because students, they understand, okay ma'am, I have understood that, but I don't know ma'am how to remember all of these. So this is the coordination number 4, right? Here all these are where POS is present, that's why optical isomerism is not shown here. All these are where POS is present, so optical isomerism is not shown in the, and always remember, in coordination number 4 we are talking about tetrahedral. We are not, because see square planar if you see na, square planar if you see, square planar no matter what, there will always be a plane that is passing through this. So square planar always will have, even if all of them are different, even then it will always have a plane which is symmetrical. That is why we are not going to do that, right? That's why I have given you this simple thing here, that here MABCD will not have any place. This is a tetrahedral. This is not square planar. This is tetrahedral. Square planar never will going to show you any optical isomerism. In tetrahedral you have MABCD and you have MAB twice. They are not going to have any POS. You can also check that out. If I say MABCD, if all of these are different, this plane, there is no plane that is going to have the symmetry, right? Okay. Then for coordination number 6, right? For coordination number 6, here POS is, let's say here it is shown by, wait a minute, here this will also show, this will also show, wait a minute, let me just do that. MA2, B2, C2 will give you optical isomerism. So this one is important, MA2, B2, C2. Then you have MA3, B2, C. Here you will have no optical isomerism, but in case of MA, B, C, D, E, F, which were giving you 15 geometrical isomers that we have seen, each geometrical isomer will give you optical isomer, right? So that's why 15 multiplied by 2, total optical isomer is 30 and total stereo isomer will be also 30. Because geometrical isomer you have calculated here only. Optical, see this is A, right? And this is the optical isomer of this A. So they both are optical isomer. This was also GI. So that's why it will not be 45, it will be total 30 stereo isomers. In case of A4B2, this is important. In this case, you have, in this case, whether it's trans or it cis, it will not show any optical isomer, right? Now one by one I am going to tell you the ones which shows optical isomer. I have drawn some diagrams here. If you have MAA thrice, that is you have, this is very important question that has been asked so many times. So I am only giving you some important things here, right? In this case, remember that here you have X, here you have Y. Let's say this is X, this is Y, this is Z. When you take the mirror, this will be Y, this will be Z, this will be X. Because here Y, ma'am, it is not showing any POS, reason because of its axis. When you rotate it, this is cobalt, okay, I want to rotate it. I want to rotate it by 120 degree. So this will become X. I want to rotate it by 80 degree. This will become Y and this will become Z. Can you see earlier this is X, this is also X. This is Y and this is Z. This is Z and this is Y. So X's are different. That is why on rotation they are not getting superimposable mirror images because X's are different. So they are non-super mirror images. That is why optical isomer is present in this case. Then in case of A2B2, you have only cis form is optically active. So this is the cis form, this is X and this is Y. When you take the mirror image, this will become X, this will become Y. And when you take the this will actually go here, this will be opposite to this one, that will go here, this is X, this will go here, that is Y, and this will become Cl and Cl. So X is overlapping Y, Y is overlapping X. So they are non-superimposable mirror images. That's why they are optically active, right? Then you have AA, B2, C2. Here also cis form is going to give you optical isomerism, trans form is not going to show you in the similar way, right? Okay. Then what is the trick for optical activity? Same type of ligands. If you have same type of ligands as a trans pair, that is this is metal, this is A and this is A, it is always going to have a plane of symmetry, right? Always plane will pass through that, so always it is going to be optically inactive because always POS will be present here. If you have more than one same pair, like you have AB and AB, in this case you can directly say POS will be present here as well. So in all these two cases, this is a trick where you can identify that POS will be present. Now guys, these are the charts from where you can remember the optical and geometrical isomers that I'll provide you in the PPT, right? Now let's do some questions based on isomerism. Here it is. Consider the following reaction and statement. So this reaction is given to you where they're saying two isomers are produced if reactant complex is a cis isomer, two isomers are produced if the reactant complex is a trans isomer, only one isomer is produced if the reactant complex is a trans isomer. The correct statements are out of these, okay? So one by one we will see that this particular compound they are talking about, which is a cis isomer. If I say this is a trans isomer, it will be this one, right? Now when you see when it is reacted with Br, it will give you facial and meridional, two isomers it will give you when this is reacted with Br here. That means it will become Ma3B3. So replacement can be either this will be replaced, if this is replaced it will find this one, right? If this is replaced, then you will find this one, right? So two things are possible, but in this case when you have trans isomer, right, only one possibility is there, that is this one, right? So only one possibility is there, that only this particular position can be replaced. See, even if you're like, ma'am, I want to replace this, that will give you the same thing. Even if you replace this, that will give you the same thing. Even if you replace this, that will give you the same thing. So always it is going to give you the same thing, no matter which ammonia you replace by Br, always it is going to give you the same answer here, right? Here if you replace this, it is going to give you a different answer if you replace this. Similarly, if you replace this, it is going to give you facial. If you replace this, it is going to give you meridional. So I can also write it here. It is going to give you facial. This will give you facial. This will give you meridional. So that means Here, all of them will give you only one thing, that is meridional. Whether you replace here, here, here or here, same thing will be there, right? Okay, so that's the reason you have 2 and 3. Let me see. Two isomer produce if reactant complex is cis isomer. Yes. Two isomer produce if reactant is a trans isomer. That is incorrect. Only they are asking you correct statement. Na? Only one isomer is produced if it is trans isomer. That is correct. Only one isomer is produced if the reactant is cis isomer. That is also incorrect. So 1 and 3 are correct. So answer will be C is the correct answer here. Right? Then guys, we have next question, that is JEE 2025. A homoleptic octahedral complex forming using monodentate ligand will not show any stereoisomerism. Now they are saying homoleptic octahedral complex, right, where all the ligands are same, Ma6, right, forming monodentate ligands, we have seen that this will never show any stereoisomerism, nor it will show you GI, nor it will show you, neither it will show you any optical isomerism. So this is the correct statement. Cis and trans platin are heteroleptic complexes of PD? No, they are complexes of PT. If you see this here, they are the complexes of PT. Yes, they are heteroleptic, but they are complexes of PT, not PD. So we can say that first statement is true, but the second statement is false here. Wait a minute, let me just write it. Both are not. Statement 1 is true, statement 2 is false. So answer will be A is the correct answer, and that's it. I have taken some extra minutes here, I know that, but we have completed this particular chapter with everything I have done. Right from this chapter, if you see this 1.5 hour lecture, you are good to go for your exam, right? You are really good to go, right? Now, what I want from you guys on Sunday, that is tomorrow, I'll be doing GOC from organic chemistry. In a short manner, I'll teach you stability of intermediates, acidity, basically everything, right? So it takes a lot of energy, right, to complete these kind of sessions in just very less time so that you can save your time, right? And guys, our crash course is going to launch on this 5th of November, and I'm really excited for that, because you know, crash course is not about that we will take a lot of time from you. It's about crash, that we will teach you some tricks, some important concepts. And in this crash course, we are going to teach you high weightage topics in detail with tricks and concept clarity, everything with question practice as well. Right, so everybody, we want your support as well. Write it down in the comment section, hashtag Sigma Crash Course, and spam it in the chat box as well. Now I'll see you all in the next class. And before that, remember, today is the last day to register yourself for MVSAT scholarship program, because tomorrow it is going to end. Right after that, you will not get any chance for MVSAT scholarship program, so do it right away, right? So that's it guys. Now I'll see you all in the next class. Bye bye, see you all, and do write down your amazing comments in the comment section. Bye bye, take care.